Usually, when we talk about accessing really cutting-edge technology, there's this unspoken expectation of a toll booth.
Right. Always a toll booth.
Like, you want access to a supercomputer. Cool, pay the $20 monthly subscription, send your private data through an invisible wire to some massive server farm. And the tech giants basically just point to their walled garden and say, there it is, rent it.
Yeah, and it creates this, it's a permanent state of dependency. The infrastructure is super clean. The user interface is polished, sure. But, well, you are entirely beholden to their terms of service, their privacy policies, their server uptime.
Exactly. And today we are looking at a technological landscape that is aggressively attempting to dismantle that exact toll booth. So the mission for our deep dive today is highly specific and honestly a bit subversive.
I like subversive.
Right. We are going to walk you, the listener, through the precise step-by-step process of turning your local hardware, your laptop, your desktop, and actually, eventually, even the smartphone sitting in your pocket into an offline, entirely private AI powerhouse.
Oh, yeah.
And we're doing all this using Google's brand new open source model, Gemma 4.
Which is, frankly, an incredibly ironic development. Google, a company that basically invented modern cloud infrastructure and relies entirely on centralized data processing.
Yeah.
They are the ones releasing the specific tool set required to just sever the cord from cloud computing altogether.
That irony is honestly the crux of the two source transcripts we are pulling from today. Because these are deep, highly technical reviews from developers who have spent, the last 24 hours just stress testing Gemma 4 to its absolute limit.
Right, pushing it on various hardware, running offline coding agents.
Yeah, and we're going to extract the practical nuts and bolts of how they actually did it. Because the underlying sort of unspoken secret of the AI industry right now is that big tech desperately wants to trap you in their ecosystem. But the math and the hardware have advanced so much that a model you can run for free, 100% offline, is rivaling the performance of a 1.1 trillion parameter giant.
Which is just staggering.
It really is.
Yeah.
Okay, let's unpack this. Because to understand the magnitude of that claim, we kind of have to look under the hood at what Gemma 4 actually represents structurally.
Right. And first off, this is a multimodal architecture, which means we are no longer talking about a system that merely predicts the next word in a text sequence.
Yeah.
Right?
Not just a fancy autocomplete anymore.
Exactly. The model natively processes text, image, audio, video, and raw code within the exact same neural network space. And the licensing model Google chose, which is an Apache 2.0 license, is arguably just as disruptive as the math itself.
Okay, let's pause on the licensing for a second, because I know terms like Apache 2.0 can sound like, well, just bureaucratic boilerplate to a lot of people.
Sure.
But for developers and enterprise businesses listening, the license attached to an open source model basically dictates whether it's just a fun weekend project or, a viable foundation for a multi-million-dollar business. So how does Apache 2.0 differ from the bespoke licenses we see on other supposedly open models?
Well, it's really the difference between true ownership and conditional permission. A lot of models release under custom licenses that explicitly forbid commercial use.
Right.
Or they include clauses stating that if your product reaches, say, a certain monthly active user count, you suddenly owe the creator a massive licensing fee.
So they use open source as a marketing gimmick.
Exactly. But Apache 2.0 is an OSI-approved, permissive-free software license. It means a solo developer, a healthcare startup, or even a massive financial institution can just take the Gemma 4 weights, embed them into proprietary software, modify the architecture, and sell the resulting product without ever paying Google a single cent in royalties.
Wow. So they are basically handing over the raw material of intelligence with zero strings attached.
Yep, zero.
And the sources point out that out of the box, it supports over 140 languages. But what really jumped out to me in the benchmarking data is the performance to size ratio. Because the largest version of Gemma 4 we are discussing today tops out at 31 billion parameters.
Right.
Yet, on the Arena AI Text Leaderboard, which is that blind, crowdsourced A/B testing site, this 31B model is ranking third globally. It's beating models 20 to 30 times larger. It's literally trading blows with 1.1 trillion parameter behemoths.
That's wild.
But parameter counts can sound like arbitrary tech jargon to our listener. If a trillion parameter model is like a massive sprawling university library, How is this tiny 31 billion parameter model giving us the exact same answers?
So the answer lies in the shift from data hoarding to aggressive data curation
Yeah.
and algorithmic efficiency. For the last 5 years, the industry basically assumed that bigger was inherently better.
To throw more data at it.
Right. If you wanted a smarter model, you just scraped more of the internet and threw more GPUs at the training run. You built that massive university library you mentioned with billions of books. But what researchers have found recently is that a massive percentage of those parameters were basically dead weight.
Oh, interesting.
Yeah, they were just memorizing redundant boilerplate code or SEO spam or completely contradictory information.
So a 1.1 trillion parameter model isn't necessarily a genius. It might just be a massive hoarder with a lot of noise in its head.
Precisely. Google's approach with Gemma 4 relies heavily on highly refined synthetic data and ruthless optimization. Instead of giving the model a billion low-quality Python scripts scraped from random old forums, they give it incredibly dense, perfectly annotated, logically complex synthetic reasoning paths.
Okay, so quality over quantity.
Exactly. They're maximizing the intelligence density per parameter. So when you query Gemma 4, it isn't searching through vast, sprawling corridors of redundant data. It's traversing a highly condensed, masterfully optimized conceptual map. That efficiency is why it can out-reason a model 30 times its physical size.
Man, that's fascinating. Which brings us to the hardware, I guess. Because before we can show you how to install this engine into your computer, we have to address the physical limits of the machine sitting on your desk.
Definitely.
You can't just hit download without sizing this up first. Because if you mismatch the model to your hardware, your machine will either grind to an absolute halt or just crash completely.
Yeah, nobody wants that.
Right. So the sources break down 4 specific sizes for Gemma 4. We have the E2B and E4B, which stand for effective 2 billion and 4 billion parameters. Those are the mobile variants. We will dissect a little later. But for laptops and desktops, we're looking at the 26 billion parameter model and the 31 billion parameter model. And this is where the architecture gets really technical, because the 31B model is a dense model, whereas the 26B model uses a mixture of experts, or MOE architecture.
And that distinction between dense and MOE is probably the most critical variable when setting up local AI right now. In a dense transformer model like the 31B version, the math is brute force.
Okay.
For every single token, the model generates every fraction of a word. A mathematical calculation must be passed through every single one of those 31 billion parameters.
Wait, so all 31 billion synthetic synapses are firing simultaneously, constantly, just to produce a single syllable?
Every single time.
Yeah.
It makes the model's behavior highly predictable, and it generally provides the highest absolute ceiling for complex reasoning. That 31B dense model is the one sitting at number 3 on the global leaderboards, but the computational cost is staggering.
I can imagine.
The memory bandwidth required to move the data for 31 billion floating point numbers across a silicon chip, dozens of times per second. It requires massive hardware power.
And the sources outline exactly what that cost looks like in terms of memory.
Sure.
An uncompressed version of the 31B model, what they call BF16, weighs in at a massive 63 gigabytes of file size.
Which is huge.
Yeah, to run that at full precision, you would need a dual GPU setup that most consumers just do not have. So the community uses quantization. They compress the model down to a Q4 or 4-bit integer, which drops the memory requirement down to about 16 to 20 gigabytes.
And we should probably unpack what quantization actually is, because it sounds like we are just zipping a file, but it's really a mathematical transformation.
Right.
The model is trained using 16-bit floating point numbers. These are highly precise, incredibly long decimal values. Quantizing to 4-bit means we are rounding those precise decimal values down to much simpler, blockier whole numbers.
But doesn't that just destroy the intelligence? Like, if you are rounding down the very math that makes it smart, shouldn't the reasoning just fall apart?
You would intuitively think so, yeah. But the neural network is remarkably resilient. We've basically discovered that the relative relationship between the parameters is way more important than the absolute precision of any single one.
Oh, that makes sense.
Right. As long as the mathematical shape of the network stays intact, you can strip away vast amounts of precision. You lose some nuance, maybe it struggles with obscure trivia, but the core deductive logic remains completely functional. Honestly, quantization is the only reason consumer hardware can even participate in this right now.
Okay, so that is the Thun1B dense model. Brute force, heavy memory. But then we have the 26B model, which uses the mixture of experts, or MOE, architecture.
Yes.
Let me float an analogy here to see if I'm grasping this. If the dense model is like a massive general contractor trying to do the plumbing, electrical, and framing all at once for every room,
Yeah.
is an MOE model more like having a specialized team? Like, if I ask a coding question, only the coding expert steps forward, saving energy and memory.
What's fascinating here is that your analogy is spot on conceptually. Though the computer science is a bit more granular, it's less like hiring specialized contractors and more like walking into the triage center of a massive hospital.
Okay, triage. I like that.
Right, because the most critical component of the MOE model isn't just the experts themselves, it is the routing network. When you feed a prompt in, it doesn't just wake up one single expert. The router analyzes the prompt and uses a routing algorithm, and it might say, okay, this token needs 80% input from the linguistic reasoning expert and 20% from the spatial logic expert.
And the other experts just sleep.
Exactly.
Hmm.
The parameters dealing with audio processing or French translation are bypassed entirely.
So it's dynamically blending the outputs of just a few specific subsets on a token-by-token basis.
Yep. The 26B MOE model might only activate 4 to 6 billion parameters at any given millisecond. This sparse activation means your computer only performs math on 6 billion parameters instead of 31 billion. So inference speed skyrockets and the active memory strain plummets.
Which perfectly transitions to the actual hardware realities the sources talk about.
Yeah.
Because if you are running a standard Windows or Linux machine with an NVIDIA card, you are reliant on VRAM, right? Video RAM.
Yes, exactly.
Standard RAM is just too slow for that volume of data.
Yeah.
To run these 16 to 20 gigabyte quantized models comfortably, you need around 24 gigabytes of VRAM. For context, an NVIDIA RTX 4090, which is like a $2,000 enthusiast card, has 24 gigs. It's a massive bottleneck for normal PC users.
It really is.
But the transcripts highlight this crazy structural advantage for Mac users. Apple Silicon and the M1, M2, M3, M4 chips, they completely bypass this VRAM bottleneck.
It is arguably the most significant hardware advantage in the consumer AI space right now, because traditional PC architecture separates the central processor and the graphics processor, right? They sit on different parts of the motherboard and talk across a bus.
Yep.
The GPU has its ultra-fast VRAM, and the CPU has its standard DDR system RAM.
And moving data back and forth across that bridge introduces massive latency.
Precisely. But Apple Silicon uses a unified memory architecture. The CPU, GPU, and neural engine all sit on the exact same piece of silicon, pulling from the exact same pool of memory.
So if you have a MacBook Pro with 64 gigs of unified memory,
The GPU can just instantaneously allocate 50 gigabytes of it to load a massive model. A standard laptop suddenly possesses double the VRAM of a $2,000 desktop graphics card. And the memory bandwidth is insanely fast.
it's basically an accidental monopoly on local AI inference. They built it for video editing, and it just happens to be the mathematically perfect layout for large language models.
Pure coincidence, but a very happy one for Mac users.
But to be clear to the Windows and Linux listeners, you are not locked out. The sources note that by utilizing the highly quantized Q4 versions of the smaller MOE models, you can run localized AI on as little as 3 to 6 gigabytes of VRAM. You just have to choose a lighter model.
Right. There are options for everyone.
Okay, so we've sized up our hardware. No, we're going to actually install this thing. We promised you we'd keep it simple, but it is time to face the terminal.
Ah, the terminal therapy session.
Exactly.
Okay.
I know the terminal looks like the Matrix and feels intimidating for a lot of people, but think of the terminal just like a restaurant kitchen. The graphical user interface, your mouse, your folders is the dining room menu. It's safe. It's curated.
You can only order what they let you click on.
Right. The terminal is just you walking past the host stand directly into the kitchen and giving explicit, raw instructions to the chef. No menus, no safety rails. And step one for doing this is super easy. Go to ollama.com.
Yeah, Ollama has fundamentally democratized this process.
The sources mention other options like LM Studio or llama.cpp, but Llama is just best for pure simplicity. So step 2, download the client for Windows, Mac, or Linux. It's about a 1.7 gigabyte download. Run the installer like any normal app.
Super standard.
Step 3, open the terminal on Mac or Linux or Command Prompt or PowerShell on Windows. It's just a blank window with a blinking cursor.
And this is where you run the magic one-liner.
Step 4, you type Ollama, run Gemma 4231B, and you hit enter. That is it.
It's honestly amazing. And if you ever get stuck, like literally just opening the terminal, ask any AI chatbot, how do I open the terminal on my machine? Don't let the lack of a shiny UI stop you from unlocking this computing power.
Absolutely. So what happens when they hit enter?
The system automatically reaches out, finds the exact quantized weights for Gemma 4, and downloads the model file. Takes a few minutes, depending on your internet.
And these use that GGUF format, right?
Exactly. GGUF is brilliant because it packages all the metadata, the tokenizer rules, the parameter definitions, right alongside the math weights. So you aren't just downloading a block of math, you're downloading the instruction manual on how to read it at the same time.
That's super efficient. And you can also just type Ollama list in the terminal to see what models you have installed. But once it's running, you just type in the terminal like a normal chat box. And the sources say on a MacBook, this can output 40 to 50 tokens per second.
Which is blindingly fast. And just to clarify, a token isn't exactly a word. The model understands math, not English. So it breaks language into chunks. Apple might be 1 token, but unbelievable might be 3. Unbelieve and able.
So 50 tokens a second means it is generating complex thought faster than you can physically read it, all offline.
Completely disconnected from the internet.
Okay, running it in the terminal is undeniably cool. But for the listener who wants to actually build things, we need to plug this localized brain into a developer workspace. We need an offline coding agent.
This is the leap from a cool party trick to real enterprise utility.
Right, so to make your local Gemma 4 talk to coding tools like Hermes Agent or Cursor IDE or OpenClaw, we need to serve it.
Yes. Step 1 is the server.
So you open a fresh terminal window and you type Ollama serve. It creates a local API. And the magical string you need to remember here is your local host port, http://localhost.11434v1.
Let's break that down because it's important. Localhost means your computer is explicitly blocked from reaching out to the broader internet. The OS intercepts the request and routes it right back into your own machine. You're talking to yourself.
Right. And port 11434 is just Ollama's channel, and the V1 makes it mimic the OpenAI API structure, right?
Exactly. It's brilliant. Any software built to talk to ChatGPT can be tricked into talking to your local Gemma 4 just by swapping the web address for that localhost URL.
Okay, so step 2 is the agent. Let's use Hermes Agent as the example. You open your IDE, like Cursor or VS Code, open the integrated terminal inside the IDE, and run the one-line install command from the Hermes GitHub.
Super straightforward.
Then step 3 is the handshake. Once installed, you type Hermes model to configure it. Select custom endpoint. Paste in that exact localhost URL. And here is the crazy part. Leave the API key blank.
Yep, just leave it empty.
Because it's completely local. There's no server checking your identity. You just select the Gemma 4 model from the list, and you're done. The sources also mention you could use OpenClaw via PowerShell, or this super minimal agent called py.dev, which might run faster locally, but the process is the same.
Exactly the same.
Now here's where it gets really interesting for me. By pointing our coding tool to localhost instead of a cloud server, we have essentially severed the umbilical cord to the internet, right?
Yes. You are no longer wiring APIs, managing credentials, or paying per token. You are doing what the sources call vibe coding.
Vibe coding, I love that term.
Right. You can do deep multi-file code generation on an airplane, in the woods, or simply in absolute privacy.
But wait, let me push back a little. If I ask my offline agent to build a React app, doesn't it need the internet to get the newest documentation or syntax? Aren't I trapped with a model whose knowledge froze on its training date?
It's a valid concern, but the developer community solves this with localized RAG retrieval augmented generation.
Oh, right.
Even though the model can't browse the web, your IDE can index your local workspace. So if you download the latest framework documentation as a text file and drop it in your folder, the agent reads it locally, updates its context window, and writes code based on the new rules.
That's amazing.
And honestly, the lack of internet isn't a bug here. In enterprise environments, it is the entire value proposition.
Because of zero trust environments, right?
Exactly. Think about defense contractors or developers handling high-pay compliant healthcare databases. For years, they've been forbidden from using generative AI.
Because pasting proprietary code into a cloud API is a massive NDA breach.
Yes, it's a data exfiltration nightmare. But by utilizing Ollama and routing everything through local hosts, the data physically never leaves the silicon on your desk. You get all the productivity gains of AI development with absolute cryptographic isolation.
Okay, so we have it installed and we have it wired to our tools. What can it actually do? Let's look at the stress tests from our sources.
These are pretty mind-blowing.
The first one was a vision to code test. A tester gave the 30B multimodal model a complex architectural diagram of an Amazon cloud setup. Whiteboard stuff.
Right.
Load balancers, WordPress instances, Redis caches, S3 buckets.
Which is a non-trivial infrastructure design.
Right. And at about 200 seconds, maxing out that 24 GB VRAM, it didn't just describe the picture, it perfectly generated the Docker deployment files needed to actually build that infrastructure.
Just from the image.
Wait, really? Just from a picture of a whiteboard? That's like handing someone a photo of a cake and them instantly writing the perfect recipe.
Yeah.
How does it bridge the gap between a messy arrow on a whiteboard and functional Docker syntax?
Well, it uses vision transformers. It slices the image into tiny mathematical patches, identifies lines, text, spatial relationships, and maps them into the exact same space as its language data.
Okay.
So when it sees an arrow pointing from a web server box to a database cylinder, its attention mechanism correlates that visual relationship with its vast training data on network topology. It knows that connection requires specific environment variables and port bindings in Docker, and it just generates the syntax.
It synthesizes functional logic from visual intent. That is wild.
It really is acting as a senior systems architect.
The second test was a UI generation split test, generating web components from a reference image. And they compared the 31B dense model against the 26B MOE model. You'd think the bigger 31B model would easily win, right?
You'd intuitively think so, yeah.
But the 26B MOE actually outperformed it. It was way more accurate with spacing and even captured the stylistic vibe of a handwritten font used in a review section.
Which perfectly illustrates the advantage of specialized routing. The dense model processes everything through all 31 billion parameters. It's an averaging machine. The sheer volume of general knowledge can sometimes dilute the specificity of UI design.
Okay.
But the MOE model isolates the query. It aggressively weights the parameters explicitly trained on CSS and design semantics, silencing the billions of parameters dedicated to backend Python or trivia. Sparsity creates focus.
Sparsity creates focus. I like that. Okay, the third stress test was about logic and reasoning. They gave it a networking puzzle, basically. I mapped port 80 to an internal IP, 192.168.2.220, but the outside world still can't access my site. Why?
A classic infuriating diagnostic test.
Right. And the model flawlessly deduced that the issue might be a carrier-grade NAT issue or CGNAT, meaning the internet provider is using a private 100 prefix IP overriding the local router.
Deducing that locally, without querying a search engine, proves the model possesses genuine diagnostic reasoning. It's not just text retrieval, it's traversing a complex logic tree.
And the last test was an autonomous agent workflow. They told it to automatically grab the top 5 AI news stories from Hugging Face, translate them to Chinese, and format them into a markdown file for WordPress. And it did it perfectly, all offline.
Which really demonstrates the React prompting framework reason and act. Maintaining that context window across multiple distinct cognitive tasks, fetching data, translating, formatting, is the hallmark of a highly capable agent.
Incredible. And, okay, everything we've talked about so far has been anchored to a desk, right? A desktop workstation or a massive laptop. But the sources reveal a final side quest that honestly borders on science fiction. We can take this exact same architecture and put it directly on a smartphone.
Yep, Gemma 4 in your pocket.
So how do we do this? You don't need the terminal for this one. You just go to the App Store on iOS or Android and download the official Google AI Edge Gallery app.
And you have to be careful here. Make sure to select the new Gemma 4 models. Don't grab the older Gemma 3 ones buried at the bottom of the list.
Good tip. You get 2 choices. The E2B model, which is about 2.5 gigabytes of storage, or the E4B, which is 3.6 gigabytes. And these run entirely locally on the phone's chip.
Right. They're heavily quantized, specifically distilled to run within the severe thermal limits of a phone. You can't put a massive cooling fan on an iPhone.
Right. But even so, in the tests, it was running at about 30 tokens per second. And the E4B model was able to generate usable pricing page web components just from a reference image, all running locally on an iPhone 16 Pro Max in airplane mode.
The shift to edge inference is massive. It's using the phone's neural processing unit, or NPU, to do the math highly efficiently.
Okay, the source video mentioned this could save your life if you're injured in the woods without a signal and need medical advice, but honestly, I'm just picturing myself coding a video game on a camping trip.
I mean, both are valid.
Yeah.
But if we connect this to the bigger picture, the reality is that a 4B model on a phone won't beat massive cloud models for intense enterprise math. But having an offline, highly capable reasoning engine in your pocket democratizes AI in a way we haven't seen yet. It's the ultimate backup brain. It can't be throttled, it can't be censored by a network outage, and it fundamentally cannot leak your queries.
It's just permanently yours.
Exactly.
Well, let's recap this journey we've been on. We started by understanding the Gemma 4 architecture and why a 31 billion parameter model is punching way above its weight class.
We conquered the terminal anxiety using Ollama to download and run the models locally.
We linked that local AI to the Hermes agent by pointing it to localhost on port 11434, essentially creating a private offline developer workspace. And finally, we looked at taking the smaller E4B versions on the go with our smartphones.
It's a complete paradigm shift.
It really is.
Yeah.
And I want to remind you, the listener, that all of this, the models, the software, the tools, is completely free. It's private, and it's yours to command right now.
Which leaves us with a pretty provocative thought to mull over. We've spent the last decade building thin clients devices that rely entirely on the cloud to do the heavy lifting. But if a smartphone can run a multimodal AI offline today, what happens to the multi-billion-dollar cloud computing industry tomorrow when every single device becomes entirely self-sufficient?
The toll booths become obsolete.
Yep.
Because you just downloaded the blueprints to build your own engine. Thanks for joining us on this deep dive.